Okay, so this is the compound interest formula we used the other day. Now there's a limitation on this. This can handle an n value of, once a year, twice a year, 12 times a year, monthly, even daily, 365 days a year. This formula can handle that just fine. But if there was such a thing as continuous compounding, which there actually is, some banks offer that on some products, this formula falls short. You can't put infinity down there for n. It just doesn't work. So just to understand what number we're going to use in the formula, this is just for understanding. The first page, you don't have to write your notes. No need for that. So if I plug in, let's see, an n different, I'm going to plug in different n values. Like I'm going to choose like 1, maybe 10, 100, 1,000, and maybe even go up from there. But we're going to plug in values for t, p, and r as 1. So this is going to be 1 plus 1 over. So basically, if you do that, if you plug in those values, that would be p is 1, 1 plus r is 1, n is still n, and n times t is 1. So it ends up being this formula, if that makes sense. So that's what we're doing here. We're keeping all those other values constant. And we're going to get, so let's just get this calculator ready because we're going to need it here in a second. So 1 plus 1 over 1 to the power of 1 is 1 plus 1 is 2, 2 to the first is 2. So we get 2, okay. Let's see if this increases when we put a much larger value here. So 1 over 1/10 to the 10th. So this will be, so let's just type that on in our calculator here and see what happens. So that'll be 1 plus 1 over 10. I'm going to put a decimal point because I want a decimal point in my answer to the power of 10. Whoops, to the power of 10. So that's 2.59. Okay, and then we put on 100. So I'm going to copy it. Whoops. Sorry. Okay, here we are. Get back to my calculator. So if I copy and paste, plug in 100 there, plug in 100 there, and I get, so if I plug in 100, I get 2.7170. Plug in 1,000, let's try that. Plug in 1,000 for it up in the numerator or the exponent spot. So what's interesting is it's not increasing that much. Do you see how much it slowed down? It started at 2 and going up by leaps and bounds here. Let's just put like 1 with 6 zeros here and see what happens. That's 1 million. Okay, so if I put a million, why do I keep doing that? Gotta get my calculator screen over here. So that right now it has 3 zeros, so I want 3 more zeros and 3 more zeros here. And it doesn't go up that much. Like it looks like we've reached very close to, 0.71828. I mean, put it in a million. That's an awful lot. It's kind of slowing way down. Like it's almost stopping. It seems to be approaching a limit, or almost like an asymptote. Like it's approaching some value, and that value is actually E. So it's called Euler's number. If you type E in your calculator, the calculator actually has a key for that, I think. So there's an E to the X key right there. So if you put E to the 1, I'm going to put a decimal point so I get a decimal. Is 2.71828. Wow. It actually goes down, whenever you grab a number, it's more numbers than just that. It's an irrational number, kind of like pi. It's actually super famous. So as you get towards calculus, you'll actually use E a lot more than you use pi. Geometry, you use pi more, but this is the number going forward that's actually more famous in math as you get into higher math. And it's got a lot of neat properties. I'm going to save some of those for calculus because there's some nice reveals you get with that. But that is a number we're going to use in our formula. So the formula, we'll come back to the graphing in just a minute, is this. So E is actually not a variable there. That's the Euler's number. That's 2.71828. Your calculator can just type it in. But that's part of our formula here. So this is a formula only when compounded continuously. So this is a special formula because our other formula can't handle continuous compounding. And just see if this is, it's not that much better, but it's a little bit better than just kind of like it was compounded from 1 to 4 times a year is a little bit better. So let's just plug into the formula. So A of t, so A of 3 would be after 3 years, you would have how much money? 1,000 is put in, that's your principal, times E to the power of R times T. So R is 0.12, always use the decimal in the formula when using the formula version, and then T is 3. So then you just get your calculator out, and you go, let's see, so 1,000 times E to the power of 0.12 times 3, which is 1433. And part of the reason you're getting so much money right there is your interest rate is 12%, which is pretty crazy. So that's the formula that you need for compounding. So let's just compare these two rates. So the 5% is compounded continuously, but the 5.125, so you get a little better interest rate, but it's going to be compounded semi-annually. So let's see how much you'll get with these two scenarios. So let's say that you put in $1,000, and let's say that you do this for 10 years. Let's see which one's the better deal here. So this will be the amount using the formula, the first formula, the one we learned last week, basically. So A of t equals principal, which is $1,000, times 1 plus R over N. So this would be 0.05125 over N, which is compounded semi-annually, which is 2, to the power of NT, which is 2 times T, which is, I guess this is 10. I have 10 right there. So 10 is T, so 10. So let's figure that out using our calculator. So we have 1,000 times 1 plus 0.05125 divided by 2 to the power of 2 times 10. So this way you get 1658.72. Okay, let's use the PERT formula. So this would be 1,000, I think we start with, times e to the power of RT. So this one is 0.05, so less of an interest rate, the same number of years, since it will be 10 years. And you get 1648.72. So it's interesting, you get $10 less. That's not much less, but look at the interest rate there. It's pretty different interest rate here. So you can see it does make a difference to compound more often. I mean, it's almost like a 0.1% interest better, so to speak. Okay, so for the parent graph for this, it's going to be a very similar graph to 2 to the x, because think about what E is. E is approximately equal to 2.718. So the parent graph is y equals 0, has a point at 0, 1, and the graph looks like this. It goes up pretty fast. So it looks very much like our parent graph when A was bigger than 2, like 2 to the x, 3 to the x, 4 to the x, 5 to the x, etc. So let's just see if the parent graph is going to move. You can tell this is moving to the right 1, it's moving right 2, up 1. So if you do the parent graph, so parent graph is y equals 0. Normally the point is at 0, 1. Okay, so if we're going to move, and that normally the graph kind of has this look to it. I'm just doing the parent graph first. So if we move everything 2 to the right now and up 1, so to the right and up 1, my point is now at 2, 2. So I like to follow that point. The asymptote moved up 1. So now it's at y equals 1. Always draw that before you draw your graph. And it's going to look kind of like this. Hits that point and starts boogieing up pretty fast. Something like that would be your graph. You guys have graph paper here, but make tick marks. You can kind of do without a little bit here. Okay, so on this one, again, start with the parent graph. So y equals 0. Goes to the point 0, 1. Has this kind of behavior to the parent graph. Okay, so we're going to graph our graph. And this is an a value of 2, and there's a reflection. So you really have 2 things to do there. So all the y values are multiplied by 2, so that was at 0, 1, now it's going to be at 0, 2, so it's going to cross there. The asymptote, so I'm doing the halfway graph so far, so I'm just doing that 2. So now it looks kind of like this. But we still have one more transformation to do. So now this is going to be reflection across the reflect across the y-axis. So you take that graph and reflect it on the y, so it's kind of decaying instead of growing. It goes through that point at 0, 2 and approaches the asymptote on the right and kind of is decaying quickly as it goes through. Okay, next one. Again, start with the paragraph, y equals 0. And goes through 0, 1. There's your paragraph. Okay, so it's going to do 2 things. So first, the graph looks like it is reflecting over the x-axis. So that's going to kind of start here, go through 0, negative 1. And fall down pretty quickly. And then if we do the other transformation, so this one is moving it down. I always go left to right on transformations. So that point moves down. The asymptote actually moves down as well. So now that's going to be at y equals negative 2. The point moves down 2 points. Now that's at 0, negative 3. And the graph is approaching us to the left. It's going down pretty quickly, especially after it hits that point. So those are just some basic transformations with e to the x, very similar with 2 to the x, so it's not a lot of difference there. And we have a little bit of time. Why don't we do the PSAT here? So I kind of like this PSAT for y'all because y'all are maybe actually prepared to do this one. We have the knowledge maybe to do it. So let's see. So go ahead and read that, stop it, and read it and try it. Then I'll explain it. So A is positive, I might say A is 2, let's just say B is negative. Let's say B is a negative 3. So my equation would be, I just like to put numbers in there, y equals A, which is 2, times x to the power of negative 3. Okay, so this would be y equals 2 over x to the third, if you think about it that way. So as x gets bigger, the graph is going to get smaller because the denominator gets bigger, which means the fraction gets smaller. So I don't like this graph. I don't like this graph. This seems okay. As the denominator gets smaller, the y value should get bigger. So I really like this graph. It looks to be that kind of a look to it. Very similar to our graph of y equals 1 over x, if that makes sense. You remember that graph? It has this kind of a look. This graph is going to be very similar to that one, actually. And we're only looking at the first quadrant, so it's going to have that kind of a look to it. And that's it.